Okay, this is the second part of day 2 of binomial probabilities. If we were here in person, I would be giving you all the little cups of Skittles to find what percentage of green Skittles we have. But just imagine I'm giving you a little Dixie cup full of Skittles at the moment. Hopefully we're all keeping safe though. Okay, so Skittles, parent company, says that 20% of Skittles are green. And if someone were to take a small handful of 5 Skittles and all 5 were green, what is the probability of that happening? So first of all, we want to decide, is this a binomial setting? So B's is a binary, so is there success? Success would be a green Skittle, failure would be a non-green. Is it independent? Okay, so if we take out a Skittle, then we take out a second Skittle, we haven't put the first Skittle back in. So it is not independent. We are not sampling without replacement. For n set number of trials, yeah, we're taking out 5 Skittles. And S, the same probability, it doesn't quite stay the same. But let's take a look here. So again, we said the independent condition is not satisfied because we're sampling without replacement. So they're not independent. It changes slightly each time. Okay, find the probability of getting 5 green Skittles if this is not a binomial setting. So think back to when we started probability units. I need to find the probability of getting the first one green, multiplied by the second one being green, multiplied by the third one being green. So the first one, the probability of getting one green, there's 2,000 green, because there's 20% that are green, out of 10,000. When I take one out, I now have 1999 that are green out of 9,999. If I take another green one, I'm down to 1998 green ones out of this number. Take another green one, we're down to this, and then on the fifth one, here's the probability. So I'd multiply these all together and I get 0.00319. Okay, find the probability of getting 5 green Skittles if this were a binomial setting. So if that independence one was met, then we would use this. 5 trials, and I want 5 successes. The probability of success is 0.2 to the 5th power. Probability of failure is 0.8 to the 5th, or to the 0 power, because 5 minus 5 gives me that 0. And that gives me 0.0032. Well, look at these two numbers. Look at how darn close they are. If I was only rounding to the thousandths place, I'd be happy. Even 10,000ths, I'd be good. But they're almost the same, because although the probabilities in the number 2 one, when I'm treating it not like a binomial setting, they change so little because my sample is so small relative to the population. And this gives us what's called the large count setting or condition. If the sample size is less than or equal to 10% of your population, then you can assume it's binomial. So I'm only taking 5 out of 10,000. 5 is definitely less than 10% of 10,000, which is 1,000. So I can assume it is binomial and use my binomial formulas for this because I've met that 10% condition. Okay, so now let's say we do this again, but he's going to get a huge handful of Skittles. I think I'd be sick if I had this many Skittles personally, but okay. So he has 100 Skittles from the large bin of 10,000. We're going to let X equal the number of green Skittles in a handful, and we're going to consider it a random variable, a binomial random variable, because the 10% condition is met. 100 is less than 10% of 10,000. So now we're going to use our binomial formulas, and let's see what numbers we get. So if I want to find the probability of having at most 11 green Skittles, I'm going to have to be doing the cumulative because I want the probability of getting 0, of 1, of 2, of 3, all the way up to 11, and including 11. So I'm going to be using binomial CDF, the cumulative one. The n value is 100, p equals 0.2, and x equals 11. And again, on an exam, It's perfectly okay to write this out, but you have to include this, not just the numbers, but n is equal to 100, p is this, and x is this, to show that you understand this is the number of trials, this is the probability, and this is the number of successes you desire. And we get 0.0126. Now, the approximate shape of the distribution is normal. And because it's normal, I can calculate my mean and standard deviation, or I want to calculate it. And here was my graph of what it looks like, the distribution, just so you can tell that that does look normal. To find the mean, when it's binomial, we take the number of trials times the probability. Multiply those together and we get the mean is 20. The standard deviation comes from n multiplied by p multiplied by 1 minus p. So your number of trials, probability of success, probability of failure, and then square root that, and we get 4. So now if I were going to redo problem 5, finding this probability, treating it like a normal distribution. So I'm going to be calculating my z-score and finding that probability. So again, x minus mu. So I want 11 that are less than or equal to 11. And I want 20, well, I don't want, 20 is the mean divided by the standard deviation. And I get a z-score of negative 2.25. When I go to my table, that probability is 0.0122. So again, incredibly close, whether we treated it like a binomial or as a normal distribution here. They're almost the same. Okay, so now let's take a look at the summary for today's stuff. Okay, so on the back, I'm going to talk you through these. There are two different learning things. The 10% condition, and this simply states that when you're taking a random sample without replacement, and oftentimes we can't do replacements, like you're using whatever it is you're taking out of the population, of a size little n from a population big N. So again, the big N goes for the population, the little n is for your sample, because the sample is smaller than the population. We can use a normal distribution model if small n, the sample size, is less than or equal to 0.1 times the population. So that's 10% of your population. So anytime we are dealing with a sampling without replacement, I can use the binomial distribution model provided my sample is less than 10% of the population. Second condition is the large counts condition. And we haven't quite gone over this one yet, but we can use a normal distribution to model a binomial distribution if n, the expected number, if n, the number of trials times the probability, is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So basically, if the expected number of successes, which is what this gives us, n times p is the expected number of successes, if that is larger than 10 or equal to 10, and, so you have to have both these things, and n times the probability of failure is greater than or equal to 10, then we have the large counts condition. And again, it allows us to use a normal distribution to model binomial. So even if it's not a binomial distribution, I can use my normal distribution to model it, provided I meet these two conditions and this 10%. Okay, so let's do this check for understanding. Try it, pause this for a moment, see how much you can do, and then I'm going to go over the answers for it. Okay, so we're taking a random sample of 500 high school students, and X is the number of high school students in the random sample who eat breakfast. That's the success. We want to explain why we can model this using a binary or binomial distribution. So for binary, each trial was a success. The success is defined as you eat breakfast, or a failure, no breakfast. It is not independent, though, because there is no replacement. Once I select a high school student, I don't put them back in the pool or in the population. But I get around this independence, or not being independent, because my sample size is 500, which is less than or equal to 10% of all high school students. And granted, I don't know the exact number of all high school students, But I'm pretty sure that 10% of all high school students is greater than 500. So we can say assume, or it is reasonable to assume that 500 is less than or equal to 10%. So we've met the 10% condition, which we can use to replace the independence if we don't have it. N is number of trials is fixed. Yep, we have 500 that we're sampling. And the same probability of success, the probability of success is 0.65. Okay, use the binomial setting to estimate the probability of 300 or fewer. So that's going to be binomial CDF, because it's not that I want exactly 300, I want 300 or fewer. So I would write the probability that I'm trying to find of X being less than or equal to 300. And then this is how I'm going to plug it in the calculator, binomial CDF. Again, make sure we've got that CDF. Number of trials is 500, probability of success is 0.65, and the number of successes we want is 300, or up to and including 300. And this is the value we get. So justify why we can use a normal distribution now to calculate some probabilities. It's because n multiplied by p, so number of trials times the probability of success is 325. Well, that's larger than or equal to 10. So this is my large counts criteria. This number of expected successes has to be greater than 10, and the number of expected failures has to be greater than 10. And we find that by n times 1 minus p. So 500 times 1 minus 0.65, which is 0.35, it gives us 175. And certainly that's greater than or equal to 10. So I've met my large counts condition. So this large counts condition is going to allow me to use the normal distribution. Okay, so if I want to calculate now using the normal distribution model of what is the probability of having 300 or fewer students eat breakfast, here's my normal curve. Again, I mark the number, the mean, the number I want, and I shade the correct side. I've labeled this, I should label this as number of students eating breakfast, because we should always label that x-axis. And now I'm going to calculate the z-score. So x minus mu divided by standard deviation. 300 is the desired value minus the mean divided by standard deviation. And we get a z-score of negative 2.34, which gives me 0.0095, which is, again, not exactly the same as this. But if I round it to one decimal place, they are the same. Or sorry, two decimal places, they are the same. But they're very similar. So again, because of the large counts condition, where the number of expected successes and the number of expected failures are both greater than or equal to 10, I can use this normal model to calculate my probabilities. Okay, I didn't actually show you this, but to calculate the mean and standard deviation, mean we calculate by the number of trials times probability of success, which gave me the 325. My standard deviation, I'm using the binomial method because it is a binomial, because we met the 10% condition. So n times p times 1 minus p all square rooted, and that's where I got the 10.665. Okay, you've got this. There is homework. It's not covering the whole 6.3 section because we still have not gone over geometric distribution, and we will do that in the next class. But there is homework that only has binomial probability on it for you online. So make sure you're doing the homework titled Bolger's binomial probability, okay? Have a great day. For B-Day, students, have a great Thanksgiving, and we'll see you, at least virtually, after Thanksgiving.